Okay, there's some more problems from the Chapter 6 review, homework review. And this is an Euler's method problem. And remember, we do this by kind of using these continuous little tangent approximations and keep getting closer and closer to our desired root to and within a given or desired tolerance or error, so to speak. So remember, you just set your pattern up like this, and remember we've used a little table. X, y was my initial point. This was my derivative, my dy dx. In this case, number 43 was x plus y minus 1. My delta x was, they wanted to use increments of 1/10. Alright, so they said that delta x was 1/10. And we wanted to go all the way to 1.3 to approximate that. So remember, this is going to be your delta x, and then remember delta y is just the slope times delta x, so dy dx times delta x. And then this will give you your new point, x plus delta x, so what my starting point is plus my change of x, and then y plus delta y, and then I get delta y over here. So we start with 1, 1. Okay, so the slope was x plus y, which is 1 plus 1 is 2, minus 1 is 1. And then I multiplied, and then this was the delta x, because these are 1/10. That's given. So I multiply dy dx times 1/10, and I get 1/10, and that becomes my new delta y. Or that's my delta y. So my new y is 1 plus 0.1, and my new x is 1 plus delta x. So here's 1 plus delta x, so I just add x plus delta x to get my x value. So it would be 1 plus 0.1, which would be 1.1, and then y plus delta y. Again, 1 plus 0.1 is 1.1. Then I go back. This is my next point. It now becomes my new point. I do the same thing. Now the derivative is x plus y. Well, 1 plus 0.1 plus 1.1 is 2.2. Subtract 1 is 1.2. Multiply that, it's 0.12. By 1/10, it's 0.12. And that becomes my delta y. So again, I add 1 to the x, so I get 1.2. And then I add the 0.12 to the y plus delta y, and I get 1.22. So that's my new point. I'll do the same thing again. X plus y, if I add these up, I get 2.42, and if I subtract 1, I get 1.42. Multiply that by 0.1, I get 0.142. Add that to the y plus delta y. So I'll take my y, which is over here, which is 1.22, and I'll add that 1.42. And you get 1.362, and if I add the 0.1 to the delta x, I get that. And that's where we want to go. We want to get an approximation for that, 1.3, and it ends up being 1.362. Okay, so it's just a real nice procedure to find an approximation for a solution for a differential equation when we just have the differential equation by the rate of change. Okay, that's Euler's method. Euler's method. Okay, and that would be EULERS. Okay, Euler's method. Okay. All right, and then number 55 was let's see. Well, I can do that over here. This is number 52. This is a Newton's law of cooling problem, and I'll just kind of basically. I won't do all the calculator strokes. You can do all that, I'm sure. But this is Newton's law of cooling, and this is the solution form. We did the differential equation, and we solved it. So we had T minus T sub S, that's my surrounding temperature, that's my temperature at any particular time. This is the initial temperature, this is again the temperature of the surrounding medium or area, and then this is going to be E to the negative KT, K is the constant, depending on what kind of item we're cooling. So if we look at number 52, it says the deep cooling a pie, deep dish apple pie, whose internal temperature was 220 degrees Fahrenheit. When removed from the oven, was set out on a 40-degree breezy porch to cool. 15 minutes later, the pie's internal temperature was 180 degrees. How long did it take for the pie to cool? From there to 70 degrees. All right. I'm sorry. How long did it take? Oh yeah. Oh, how long did it take for the pie to cool? From there to 70 degrees. So first of all, we have to find the constant for this particular pie. So if we look at the first part before we go to the 70 degrees, we have the internal the temperature we had for the pie after 15 minutes. So when T is 15, all right, the temperature of the pie was 180. The initial temperature right out of the oven was 220 degrees, and the temperature on the breezy porch was 40 degrees. That's my surrounding temperature. Okay. So first of all, we have to identify these. And I told you a lot of times in these problems, you've got 1, 2, 3, 4, 5 unknowns. They'll give you enough information to find one, and then you put it back in. They'll give you 3, and they'll give you 3 or 4 things. You have to find the fourth. So first of all, we have to find K. That's going to tell us how this particular soup behaves. Okay. So we'll put this data into Newton's law. Okay, this was my temperature after the 15 minutes. This was the surrounding temperature. This was the initial temperature. This was the surrounding temperature. We used that twice. And e to the negative k, and this was the time, 15 minutes for this to happen. So then what's 80 minus 40? 140. Then I can divide what's 20 minus 40? 180. So I can divide both sides by that. And I can reduce that. So that's this binomial divided by that binomial in simplified form. Okay, 140 over 180, and I can reduce that by 10 and then also by 2 to make it 7 over 9. That equals e to the negative 15k. So I can take the natural log of both sides. Okay. Let's get, here we go. So that's 7 over 9 equals e to the negative 15k, that is. Okay, and then we'll take the natural log of both sides. And then we can put the negative 15k in front, and we'll have the times the natural log of e. And the natural log of e is just 1. Right? So we take the natural log of both sides, we end up with the natural log of e. Okay? And then, so this is 1, so I can take this in order to solve it for k. I would divide by negative 15. So there's your natural log of 7 over 9 divided by negative 15. Now, that's going to be my k, so I'll put that back in the original equation. T minus t sub s equals t to the 0 minus t sub s, e to the negative, and this whole thing. K. 7 over 9, negative 15, times t. Okay? Now, what we're going to do is after 15 minutes, it was 180. So I'm going to go from 180 to figure out how much longer it's going to take for it to cool down. I can put a 220 in there, but then I would have to subtract 15 minutes from that time because I'm going to get 15 minutes more. So here we're going to use the 15 minutes, and we're going to start here. So now my new T sub 0 is where I'm now I've cooled down to 180 degrees. The surrounding temperature is still 40 on the breezy porch, and the initial temperature was, let's see, yeah, the initial temperature from my experiment now is 180 because I've cooled down to that. This is the surrounding temperature, and this is the temperature we want it to be, 70 degrees. And we want to know when, so we're going to be looking for time. And we still got that constant in there. Okay? So I'll do like I did before. I'll simplify this. 70 minus 40 is 30. 180 minus 40 is 140. And I can reduce that by 10, so it ends up being 3/14, and that's this whole thing. Then I'll try to solve for t. That's what I want to do, is find out how long it will take. So what I'll do is I'll divide both sides by, well, first of all, let's see. Let's see. So this reduces it to be 3 over 14. Oh, sorry, this was 30. So 70 minus 40 is 30, and then 180 minus 40, pardon me, is 140, so I divide both sides by that. So I've got this divided by that, which is 30 over 140. Then I can reduce it by 10, and that's about all I can do is 3 over 14. Can I find t? Yeah, that's easy now. I just want to find out what the time is. So I take the natural log of both sides. I get the natural log of 3/4 equals the natural log of this whole thing. Well, actually, it was the natural log. I kind of skipped a step. I took the natural log of both sides, so I got the natural log. Well, no, I didn't. The natural log of 3 over 14 equals the natural log of e to the of 7/9 over 15t. Okay, because these negative signs did cancel, so that's why that's positive. except it's going to end up being negative because of its values. Okay? So again, I take the natural log of both sides, and then I can put this in front. It looks like it's a factor, but it's an exponent. I put this in front of the e, and e goes to 1. So I just have the natural log of 3 over 14 equals the natural log of 7 over 9t divided by 15, and that would have been times the natural log of e. And I guess I could write that. So you can see if I just move this in front, I would have times the natural log of e, but this would go to 1 anyway. All right? So then if I want to solve for t, I would multiply both sides by 15, and then divide by the natural log of 7/9. Then if you put this in your calculator, I took the natural log of 3 over 14, okay, and then times 15, and then divided by the natural log of 7 divided by 9, and this is what I got. 91.94. So hopefully you shouldn't have any trouble calculating that out. And one more, just to finish it up, we have an exponential decay number 55 over here. And we're using a carbon 14, so I always just derive it. Doesn't take long. It says carbon 14, what's the age of a sample of charcoal in which 90% of the carbon 14 that was originally present it has decayed. So first of all, I use my regular decay equation, and I know that the half-life of carbon 14 is 5,700 years, so I said y equals y sub 0 e to the kt. That's my exponential decay formula. And then I divide both sides by y sub 0, because I want the ratio of what I have to what I had would be 1/2. That would be the half-life, and that's 5,700. So then I can just take the natural log of both sides. That goes to 0, divided by 5,700. And I get k equals natural log of 0.5 divided by 5,700. Now you know the book kind of changed it around to the natural log of 2 and had a negative sign, but this way the negative sign is encompassed in the 0.5. Okay, and now I want basically the ratio of what I had to be just 10%. That means 90% decayed. So I only have 10% left. So I put that into this equation. So y over y sub 0, which equals 0.1, equals e to the kt, and I already figured out what k is. That's what I did over here. And then I just take so I just want to find out what t is. So I take the natural log of both sides, and that's the natural log of 0.1 equals the natural log of e to the kt. And then I'll bring that in front. This goes to 1. And this is the natural log of 0.5 over 5,700. So if I multiply both sides by 5,700 and divide by the log of 0.5, and then I work that out on my calculator, log of 0.1 times 5,700, enter, divided by log of 0.5, enter. I got 18,935 years. It rounds off. Okay? So that's 55. So hope those all help. If you have any questions, please ask in class on these, because you should have a good handle on all of this. And if you don't, please ask. All right? Good luck.